All right, so welcome back, everyone. We just went through TempoNest and how to do model comparison of various noise models, and also how to add new parameters to the timing model, both in a parameter file or just via the command line. And this can also be used in TempoNest to search for new significant parameters. Okay, so I think we should go back to the virtual machine now and actually put into practice those TempoNest steps 2 and 3, which was the noise model comparison. So the last thing we did in the virtual box was run TempoNest on just the white noise model. And then we viewed that in Tempo 2 and noted down some key numbers, like the reduced chi-squared value. So back on slide 22 is where we'll pick up with the commands that we'll paste into the virtual machine. But I will turn my video off and share my screen for the virtual machine first. And I just wanted to note a couple of other things before you go off and do that yourself. So here's my virtual machine. So I don't have too much more material to go through before we wrap up today. So I just wanted to point out, because I think I forgot to do this before, that there are these scripts. Well, first of all, make template.shell. If I just type cat to print what's in this, this is a shell script that goes through and runs these PSR add commands. So PSR adds everything in a given pulsar's directory, and then runs PSR smooth and PAM to frequency scrunch it, and then PSR smooth again. And this is the script that makes the templates. And unlike the other script, which is one directory higher, reduce data, you actually have the data for this. So you can try these commands yourself, and also go back to the earlier lectures to learn the pav commands to actually view the archive files. So you can look at these data if you like. There was also time pulsars. So if I cat time pulsars, this is showing the pat command that was used to create the TIM files that you're working with. So we use the .standard file, which is created in this make templates shell script. And this also shows that we're printing the TOAs in Tempo 2 IPTA format, and we're asking for these additional parameters. One of them is the signal to noise ratio. And this is actually what we're using in our select file. Yeah, okay, and so that sends it to $PSR.tim. And then finally, we have this flag data script. This is a little bit longer. This is something that it starts here. This is something that Ryan Shannon wrote. And basically, it goes through all of the TIM files. And if the TOA is between particular dates where we know that an instrumental change happened at the telescope, then it will add an additional flag to that TOA. And these flags are included as systematic offsets in the timing model. So if I go back into 0921, which is where we were working, and I cat the par file, then these jump parameters correspond to those flags that we just saw in that other script. So this flag here is one that's added to the TOAs, and then this is the size of the systematic offset in units of seconds. So this is a 306 microsecond instrumental offset in the TOAs that have this flag on them. Okay, so that's how that works. I'm just going to clear this screen now. And this may be a reminder at this point to type in history. Let's see if I can spell history, and pipe it to history.txt, just to preserve what you've done, and you should be recording all the way. Right, but what we're doing now is running tempo nest using some other noise models. So if you go to slide 22, we're going to copy that tempo nest command. I will also put it in the chat. Don't run this one though. Don't just copy and paste and run, because there's something special about it. Remember that at the end of this command, we have these curly brackets, which we need to fill in with our favorite noise model. So the rest of the command is the same as before. We've got tempo2 minus gr tempo nest minus f, the par file, the flagged tim file, the select file, and now a configuration file. We've already run the white noise model and we noted the log evidence for it. So now we're ready to add in another noise term. So for example, we can choose dash red to fit for white noise and the two parameters that describe this red noise power spectrum. So if I just choose red noise, I hit enter. It will take slightly longer than before, but still pretty quick for this pulsar. And right at the end here, you see it says writing par file to white dash red, and this is because we, in our configuration file, this was the root name at the top of that configuration file. Okay, so we have this this par file here. If we scroll up, we can find the evidence, and in this case, it's 1299.6. And if you remember from our white noise model, it was also 1299 something. But the important thing is that this is not greater than 3 more than the white noise only, which means there is no support from the data that there is red noise in this data set. Okay, so that's how you interpret that. So you can and should note this number down somewhere. Just say, oh, I ran a noise model with white noise and red noise, and I got this log evidence. It wasn't significant. Okay, so I'll give everyone a chance to run that. If you wanted to just copy and paste this, I'll just give this command in the chat. Oops. Yeah. Okay, so that's basically, I think, all we have to note for this noise model. We ran it and there was no evidence for it, so we can fairly safely ignore it. And so now we basically just hit up arrow to grab the command that we previously ran, and now we'd like to try a new noise model. So how about we try white noise and DM variations this time. So white-dm.c file. If we hit enter on that, again, you'll see it takes a little bit to do that. And it will have written the results to this new par file. If we scroll up, we can check the evidence. And again, it's about the same, 1299.6. And this is just repeating the results that I had in that slide, that for this particular data set, there's no evidence for any additional noise terms. Okay, so you would say I ran white noise and DM noise, this was the evidence. So you might go up arrow and try the next one, which is the correlated noise term, the white-e core. So each time it's the same command, you can just press up arrow to get the command back, the previous command back, and then just change the configuration file at the end. So now we'll run white-e core. All right, and once again, the output file name is changed. And if you scroll up, we have a new evidence value. This one's gone up. We have 1,300 now. But our evidence before was 1299. So this is an increase of, well, less than 1, because it was 1299 point something. So it appears it's changed, but actually if you take the difference, the difference is still less than 1. And so there's no support from the data for this correlated noise term. And that's basically it for this pulsar. If you run the analysis for your pulsars, you're likely to find some of these noise terms. And in the scenario where you have support for multiple noise terms, so let's say you run white dash red and you get an increase of a log base factor of 10, then you'd say, oh, great, there's red noise in my data. If you then run white dash DM and you see that there's an increase of 15, that means there's more support for DM noise being in your data than red noise. So what you would do is you would basically accept that there is DM noise. You'd accept whichever one is highest in evidence, and then test for the other one, or test for additional noise terms. So in that case, so yeah, in the scenario where you ran white dash DM and you got a strong evidence for DM noise, you could go back and then also run white dash red dash DM, which tests for red noise in addition to DM. And if that one, and so once you're testing that against your new base noise model. And your new base noise model is whatever you've now accepted. So if we run white dash DM and we see a very big increase in the evidence, then we accept that there's DM noise in the model. That becomes our new base model, right? So we save that log evidence, and that is now the comparison value. So when we add in additional noise terms like red noise, the evidence for red noise has to increase by 3 or more relative to that new base noise model, which would be the DM model in that case. Okay, I hope that makes some sense. I can just demonstrate on this pulsar if we run white dash red dash DM. So it takes longer because we're fitting more parameters, but we're also using more live points as well. Again, if I run that, again, I get just the same evidence value. We also have other noise models. You can just look at all the files in this config file. We have every combination of the noise terms we're searching for. So you can run them all, or you can do it in logical order, like I'm describing, where you add in the noise model that is best, and then search for additional terms. Okay, can I get a thumbs up from people if they've been able to run the white dash red, white dash DM, and white dash eCore? And let me find Zoom. I can't see any thumbs. I've lost my participants window. So
we had one thumb that I saw. 2, that's the second one I'm counting. Fatima says she's just following along on Zoom.
Okay. Okay, so we got
she's still having issues. Yeah.
2 thumbs and someone following along. All right. Okay, so
if I missed any thumbs, feel free to just show them again.
All right, so I'll say that
there's a third one now.
Oh, good. So yeah, once we have all those outputs, let's just, oops, I'm typing in the wrong place. So we can just ls this results directory now, and you can see that we have all of these same outputs, but now one for each of the noise models that we've run. And some of these we didn't need to run, like white dash red dash DM. If you don't have support separately for DM noise or red noise, then you don't really need to be running this. Okay, so you should have been running these noise models and taking note of the log likelihood, but the shortcut for this is also a command pasted in slide, was it 22? And that is the grep command, where you search for a string in some files. So if I paste this here, we're grepping for nested sampling global log evidence in results. And in fact, I can just get rid of the pulsar name. So if you had multiple pulsars in the one directory, then you could grep for a pulsar name like that. But we're just going to grep for all of the files with stats in them. And when we do that, we get this output, which tells you which file name this is coming from. So this is where you'll get the noise model. And then you've got your log evidence value. And unfortunately, it's formatted in a different way, but just, yeah, don't forget that there's this 10 to the 4 at the end of this. So this is a nice summary. You can look through here and see which one has the highest evidence. And in this case, they're all between -3 and 3. So the best model is the simplest model. It's the one with the fewest parameters. And that is simply, where is it? Oh, here, simply the white noise model. Right, so that's already the one that we've looked at in Tempo 2. So for this pulsar, we're done effectively. Let me just show you, for the sake of fun, what happens if your pulsar does have red noise and does have DM variations. So if we go into Tempo 2 like we did before, so Tempo 2 minus grplk minus f, we open up we select the par file. Oh, sorry, we want to select the results part file now. So this is after we've run a noise analysis. So let's say our pulsar had evidence for red noise and it also had evidence for DM noise. Okay, so that we would open up the results file from white-red-dm pulsar name.par. Open up the same flagged tim file, add our select file like that. I'll paste this in the chat. By the way, this won't work if you haven't run white-red-dm. Oops, I pasted. So while I'm trying to copy this bit of text, run the white-red-dm noise model if you haven't already. And then once you've done that, you can use that command I've pasted in the chat, and it will bring up the timing residuals from that noise model. Give everyone a minute just to do that. Okay, so what's key here in this new plot window? It looks very much the same as what we had before, except there's one important difference. Down here, we have red noise and DM variations. And so this is another variable that we can plot on the y-axis. So this actually allows us to visualize the red noise that the data supports. And the DM variations that the data supports. And I'll explain why this is an important sanity check. So in this pulsar, the way we'd look at that, or for any pulsar, is to select the red noise as the Y coordinates, right? So this is now displaying on the Y-axis the amplitude of the red noise as a function of whatever you select on the X-axis. So this is date, orbital phase, day of year, or year. Okay, so yeah, this is visualizing the red noise, and there might be some structure here, but it's not significant. You can see that it's the uncertainties are basically consistent with a line across.
It seems like we've lost Daniel. I was wondering if it was just on my end. Let's just hang on and see if he turns back on the call.
Okay, I'm back. Sorry about that. My internet dropped out for a little bit. Marissa, what was the last thing that you heard me say?
I can't for the life of me recall. Sure. Anyone else?
So I was, well, when I think I dropped out, I was talking about red noise here on the y-axis, but I wasn't actually paying attention for when I might have lost connection.
All right, I think you best take it from where you remember.
Yeah, that's right. You stopped there.
I stopped here.
Great, thanks.
Yes.
Okay, excellent. So yeah, we're visualizing the red noise here on the y-axis. And you can see here that the uncertainties are very large, and in general, these points seem to be consistent with 0, which is probably why we don't have any support from the data for this noise model. But you may see, or you're likely to see, some structure recovered in the other pulsars that you analyze. And this is an important sanity check, because if you look at your red noise as a function of, say, day of year, and you see an annual sinusoid, then that could suggest that the noise is not actually red noise, it's like a position error or something. And so really, your measurement of red noise was spurious just because you had an error in your timing model. Now that's unlikely because, unlike in this pulsar, in your pulsars, you will be fitting for the position because you have enough data to do so. But it could happen for other parameters. So for example, if you click on orbital phase, you might see some structure. And so this is just a sanity check to look out for. If we click on the DM variations on the y-axis, you see here that they have massive uncertainties and they're consistent with 0. This is, they're essentially just saying that we're not measuring any DM variations. But in your pulsar, if you do have significant DM variations, you can click on this to display them as a function of date or day of year or whatever you like. And particularly if you have red noise, that should look a lot like the averaged TOAs that you were looking at in one of the first steps we were doing. So yeah, when you average your TOAs together to get very small error bars, that's where you might see low signal to noise structure in your data. And the red noise could be that. So if you were to do this, you might see that the red noise follows your averaged TOAs. Okay, so that's just something to look out for. So one other thing I wanted to demonstrate was, and probably the last thing I think I'll demonstrate, and then you can go and try this yourself and we can be in contact when you need more work or if I have more code to give you. So yeah, so we're in this directory. I want to demonstrate, yeah, so on slide 23, this process of trying new timing model parameters as well. So yeah, I said the best practice for this was to create a new output directory. So we do that by typing mkdir for make directory, and then create something like results_test. And now what we want to do is create another configuration file, but change the root directory in that configuration file so that it outputs to this test directory. So I'm going to do that by copying. See, so we copy. Okay, I'll sort of do this quickly, and then you can do it yourself by copying the command. So maybe everyone look at the virtual machine, unless you are very familiar with Unix and stuff. So I'm going to copy, go back a directory, configuration files, and I'm going to grab the white.c file. So this was the best noise model for this particular pulsar. And for other pulsars, you might have another best noise model. Whatever your best one is, grab it and copy it to where we are now. Now I'm going to open up in a text editor. So nano, well, sorry. First, I should have copied it to a different file name, just so that I understand what's in it. So I'm going to move white.c file to white_test.c file. Okay, now I'll open up in a text editor like nano white_test.c file. And this is the line I have to change. I have to change this root. So I don't want to contaminate my nice results directory. So I'm creating this new directory, results_test. And now the results of the tempo nest run will go here. And I can safely delete the contents of that file without deleting my other runs. Okay, so now I'll let everyone do that. So let me just type in the Zoom chat. So go away to your VirtualBox and do that if you haven't already. There's the chat window here. Okay, so copy. Or you can grab some commands from slide 23. Okay, so there's the commands to copy the configuration file to this new white_test. Then go into the file. You'll have to change that root directory yourself, and then make a directory results_test. And so now all we have to do is run the same tempo nest command as before. So you can just up arrow to find that. Make sure you select white_test.c file, that it will be output to the correct directory. And then the fun part is choose which timing model parameter you want to fit for. And something that isn't already fitted for. So for this particular case, we're just anything but DM. Well, any valid parameter except DM. And yeah, for valid parameters, you can look earlier on in this talk for the syntax. You can also look at the past lectures to see what was in parameter files that we used before. So anyway, I'm going to choose to fit for, let's go px, because I did that in the demonstration. Okay, so I'm just adding fit px to the end of this command. And so we'll run the same noise model. Yeah, we're outputting to results underscore test now. If we go up here, you can see that the parallax has been fitted. There's no result here, interestingly. So maybe this didn't function the way I thought it would, but I think it has, because it's changed the evidence. I'm not sure why it's not printed here. I'll look into this and see if that's a bug and contact you on Slack if it is. But anyway, we've added a parameter and the log evidence has decreased, and so that's a suggestion that we're overfitting. Okay, let me.
Just a question, Daniel.
Yep, go ahead.
Could you please show the command that you ran for the sampler? Now, just, I know it sounds like a stupid question, but did you copy the white underscore test in configs? Because I didn't see you moving it. You just changed it in the current directory.
Yeah, so good time to check the history. So what did I do? I copied it from the configs to dot, which is where we are now. And then I changed the file name. So, oh, I see what you mean. You're right. Okay, so I had pre-made this, which is why it already exists there. So you're right. You're definitely right. I should have gotten rid of /configs to use the file that is in our directory. And that should do the same thing. So if we type remove, be careful of this command, be very careful of this command. Remove results underscore test star, hopefully it asks us, yeah. So we'll ask us if we're sure we want to remove things. And yes, we're sure we will want to remove all of these files. Okay, and so we can run that command again, but with the correct configuration. So just the one in this directory, which is why where I copied it to. Okay, and same thing. We wrote the output to results underscore test, and yeah, the evidence is the same there. Okay, so basically you could repeat removing the results of that directory. There is a shortcut to do this, so you don't have to say yes, but I'm not going to teach you that deliberately. If you already know it, then you know how dangerous it is. And so you can try fitting for different parameters. So in this case, let's try DM1 just for fun. You can run that. Yeah, again, I'll check if this is an issue. And the evidence is decreased in this case. So yeah, this pulsar is very boring, which is partly why I chose it for this demonstration. The commands run very quickly and we don't have to get too deep into the noise models. But in this case, we're essentially finished. So let's just pretend that we went through this process multiple times and we checked all of the possible parameters that we wanted to test for. Then the results are that there's only a white noise model for this pulsar. So if I open up that noise model, so this is the PAR file. These are the white noise parameters printed down the bottom. So global EF stands for EFAC and global EQuad stands for EQuad. This is just a scale factor to the uncertainties. And this is something added in quadrature, and this is in units of, oh man. That's, okay, that's in log units. And it's in units of seconds, I'd assume. Yeah. So this is also a small number, but the EFAC is scaling the uncertainties a little bit before they're being averaged together. The multiple simultaneous TOAs at different frequencies are being averaged together. Okay, so basically this is the result for this pulsar. We had an initial ephemeris, which was provided, and there's one of these for each pulsar. And the only fitted parameter was DM. And there's really no evidence from this data that we should fit for any of these parameters, meaning that the value seems to already be pretty accurate. It describes the data well. And the reason for that is that simply more data was used to set these parameters. So we're not suddenly going to improve on these parameters with just 8 individual observations. Okay, and so this is what we would write up as our results for this pulsar. Say that the DM has this value, and these are the white noise parameters, and we're finished. So let me just, I think we can basically leave it there. So you can continue the noise and timing model analysis of the other pulsars, and I think Marissa will suggest which pulsar you should work on first. We'll split people up so that people are working on different pulsars. But once you finish a pulsar, you're welcome to work on one of the other ones. And if you finish absolutely everything, you finish all the timing model parameter stuff and tempo nest stuff, then we need to catch up again because there are some next steps. So let me just jump back quickly to the slides and I'll describe what was next. Okay, so after that tempo nest stage where we're testing for new timing model parameters, yeah, you can iterate that step with tempo nest and tempo 2. Basically, if you find that you need to add new timing model parameters, you should also retest the noise models. And you can do this by changing the results directory again, if you like, or using the test results directory. It's up to you. But because timing model parameters have structures that can be correlated with the red noise parameters, then you can iterate those 2 steps. If you add new timing model parameters, check for new noise models. Okay, another thing you can do, I don't have the code for it yet, code that works in this VirtualBox, that is. But another important thing to do is check the posterior probability distribution of your parameters. So the outputs of those tempo nest files at the moment are just text files to you, and they're just numbers summarized as log evidences. But in those post-equal-weights.dat file that I mentioned a little while ago, that contains all of the samples, and they can be plotted to show you your probability distribution. And it would look something like this. So this is called a corner plot. And in this lower triangle, ooh, my dog's going a bit crazy, sorry. So in this lower triangle, we have the 2-dimensional posterior probability distributions of one parameter against another parameter. And in these top plots, we have the 1-dimensional probability distributions where we have integrated over one parameter just to leave the probability of one of them. So in this type of plot, I will eventually send you the code to do that on Slack. So in this type of plot, you can visualize the correlations between parameters because these probability distributions can have elongated shapes. They can be in ellipses or they can be in other strange structures, and that will indicate that there's interaction happening between your parameters. And that's another thing to test. So I'll let you know when I have that code working, and you'll be able to visualize your posterior distributions in that way. So by the way,
and Daniel, Sam has got a question for you.
Sure.
Just a recap. Because I'm a little bit lost when it comes to fitting for the parameters. So from yesterday's lectures, we were able to fit the parameters just using the PLK on tempo 2, which is what is it? Maximum likelihood estimator, I assume. And now we're only fitting the parameters included in white noise and all different types of noise model using the nested sampler. So my question is, in the project, for any say, for instance, like from yesterday's example, the coordinates are wrong, and you can already see it from the from the GUI. So we don't do that type of fitting anymore, but we just put that parameter as a free parameter in the for the nested sampling. Or
yeah,
what I mean?
let me go back to the VirtualBox. So that's very relevant for the first steps. So back when I said we look at the parameters for the first time. Okay. So when we look at the parameters for the first time, that's when we fit for any additional parameters that we need to. So yeah, okay, so we can do the same thing here. If we, yeah, we can select these parameters and hit refit, just as you did in the past lecture, and you will see a new output with the new fitted parameter and a new chi-squared value that you could look at. But again, this chi-squared value is a little bit confusing because it could decrease, but again, this AIC test can't really be trusted for adding and subtracting new parameters if the uncertainties aren't accurate and we're adjusting the uncertainties. So yeah, in the first time where you bring up this timing model plot for a given pulsar, for every other pulsar except this one, you'll basically have all of these parameters fitted already. If you didn't have them fitted and they were at a bad value, that's when you would see this big like sinusoid or annual sinusoid, and you'll know that you'll need to fit for this position. See, in this pulsar it breaks because there's just too many parameters. But let's say DM and F1. So for the other pulsars, yeah, it will look a lot more like what you saw in the exercise yesterday, where there's all these parameters already fitted. And then when you go into tempo nest, all of those parameters are effectively sampled in tempo nest. Well, okay, they're not sampled, they don't output probability distributions, but you do marginalize over them. So you're accounting for those parameters when searching for your noise terms.
Okay.
Yeah. So adding in new parameters, it can be done on the command line as well. So even in tempo 2, so here if I say fit px for parallax, I'll now have a parallax symbol here. So this is effectively adding it to my my parameter file. Although it's actually not actually writing it to the parameter file, I would need to write press new par to save this parameter file if I was interested in this. So let's say you were looking at a pulsar and you think that there's a parallax. You add in the parallax, say from the command line or manually. And if you see that it makes, whoops, if you see that it makes a very big improvement to your timing model, and you think that that was real, then you would hit new par and give it a file name. So I'll just type new.par. And we can look at new.par and see that there is a parallax in here. And now this is nonsense because this is a negative parallax. So I shouldn't have done it for this pulsar, but yeah, hypothetically, that's another way that you can fit for the parameters. And definitely that should be done before you head to tempo nest. Basically, when you head to tempo nest to do noise modeling, you should have fitted for every parameter that you think is reasonable, because we'll be marginalizing all of those parameters in order to do to get the noise model.
Okay.
Yeah, and so if you're left with a big annual sinusoid and you're not fitting for RA DEC, then you're going to get spurious measurements in your noise model parameters. Yeah.
Okay.
Thanks.
Thanks.
Okay, thanks for the question. And yeah, I'll just again summarize. There was only a little bit left, I think, because this is stuff that I'll share with you later. So this is about looking at the corner plot, and this is a little bit special. So what do we do when we want to search for the Shapiro delay? Because eventually that's what we want to do. Because Shapiro delays are exciting. I can already say that there's not a strong Shapiro delay in any of these pulsars, but that doesn't mean that we can't constrain it. We can still search for a weak Shapiro delay signal, and even getting a weak signal is exciting, because that's when we go and simulate additional observations and we see how much more expensive Meerkat telescope time that we need to ask for, and look at this pulsar in order to get a mass measurement. So the Shapiro delay is a bit special. You can't simply just type dash fit H3 and dash fit STIG, these Shapiro delay parameters, and expect it to work. Unfortunately, they're highly nonlinear and they need an initial guess. But fortunately in TempoNest, okay, so I mean, they need an initial guess for tempo 2 because it's a least squares fitter. So if you don't understand that, you can look at the end of my lecture 4 about least squares fitting. But in TempoNest, we can actually sample these parameters simultaneously with the noise model. And that's what I would recommend we do. So just as a brief introduction, we won't actually do this today, but the way I suggest we do that is that we copy our par file to a new par file that's called _Shapiro. Within that Shapiro delay par file, we need to change the binary model from ELL1, which stands for eccentricity is a lot less than 1, to binary ELL1H. And I don't know what the H stands for, but it allows us to have these Shapiro delay parameters. Then you add these lines, H3 and some number 0, 1, and this number is in units of microseconds. So 1 e to the minus 7 is a reasonable number. Don't put like 100 here or something. Oh, sorry, this is in units of seconds, not microseconds. And then this parameter STIG. So what these parameters are, this is the, actually Federica might have got into this, I'm not sure. This is the amplitude of the third harmonic of the orbit, and STIG is the ratio of successive harmonics. And so 0.1 for a ratio is also reasonable. But anyway, these can be initial guesses. And then what you would do is you would copy your favorite noise model to another file with an _Shapiro. And within that Shapiro, okay, sorry, this should be your noise model. I'll fix that in a second. So within your noise _Shapiro.c file, you would go and uncomment those tempo prior lines that I mentioned before. So look at your par file and see what parameter number these parameters correspond to. Okay, I also realized I just got this wrong, so let me do some live corrections. So we want 1 as the fit flag. So we want H3 times that 0.1. 1 is the fit flag. And then, yeah, I'll just correct this as well. Okay, so within that C file, you would go and uncomment those tempo prior lines. So tempo prior is N and M, where N and M are the number of the fitted parameters in your par file. So if you have 8 fitted parameters and these are the last 2, then you would have N as 7, M as 8. And then yeah, you would run tempo nest then using this configuration file. And I also mentioned this before, you can go into your results directory and check your param names output file just to make sure that you see H3 and STIG are being sampled. And then once you've done that, you check the log evidence, see if there was any support for those parameters. In this case, because these are such interesting parameters, even if there's no support, it's worth looking at the corner plot to see whether there's at least a constraint on these parameters, so part of the parameter space that's ruled out by the data. Okay, but again, I can give you some more detailed instructions on how to do this and also send you the code to make these corner plots. For now, I think it's enough to just look at the initial tempo 2 timing models and work through those noise models and search for additional timing model parameters and just come up with the best solution that you can. And I'll just say that once you have a final solution, yeah, you'd note down whether you have any interesting parameters. Yeah, you can create a chi-squared grid over any interesting parameters like Shapiro delay or sample them as I described. And then once we've completely solved these pulsars, that's when we simulate further observations. And again, I can send you the code to do that, but the rough code is this. We use this fake plugin. And if you were to run this command, it would ask you for inputs like number of observations per day and the weighted RMS of those observations. And yeah, this is how you can simulate future observations. And yeah, final slide, once you're completely done and once we've finished everything, you write up your summary, which should contain all of the notes that you've been taking so far about what you've been doing, what you've found in the literature, and yeah, your final noise model, your final PAR file with parameters, and you submit a document. So just I have an example here, which I've already opened. So this is the kind of thing that you would do. So I made notes as I went along with this, this pulsar. So you might have a Google document or a Word document or whatever you like. So you'd say things like, I found this paper that analyzed the pulsar. They had these interesting numbers. They fitted for these parameters. This is the result. Here's the discovery paper. For this pulsar, I looked in the catalog and it wasn't there. And then the timing analysis. We looked in tempo 2, only the dispersion measure was fitted. It had a weighted RMS of 17 microseconds. In tempo nest, with only the DM fitted, we did a white noise only, and we got this. We looked for other terms and we got this. There's no strong support. These are the final white noise parameters. Running in tempo 2. So this is me doing a Kaki information criterion test on these parameters. We didn't talk about that. We favored tempo nest, but basically I found some significant additions to the timing model, but they were not strongly significant. And it's likely that it's because we weren't doing this simultaneously with the noise model. Okay, so that's why I said it's significant, but we'll try tempo nest. So then I tried these parameters in tempo nest as we did before. No improvements in log evidence with any parameters. So here's the final results. We have the best noise model with these parameters. The only timing model parameter fitted was the DM, and this was the result. And then you'd say we search for Shapiro delay using H3 and STIG, and insert a corner plot when you have it. So that kind of thing. And you can do this on the Slack channel as you're going through the pulsar analysis, just so people can see where you're at and if you need any help or advice. But yeah, we'd like to just collect the timing model and noise solutions for these pulsars, and if we can, constrain any Shapiro delay parameters. Okay, and I'll leave it there, and we can be in communication in the future when it's time to move forward a bit. So, any questions, I guess?
Would it be possible to get a rough timeline? Like, How long is it
Well, it would.
expected to get done? Or
Yeah, I'm not sure. There's lots of people here at different levels. So someone like Marissa, I'm sure, could probably do this in a day or less. And some other people who might be undergraduates, they might need to go through the work and take weeks of revision and to check at every stage what they're doing.
okay.
So basically, just keep updating the Slack with your results, so we can keep an eye on you. And if it's clear that you've gone through everything and you've got a solution, then I'll hurry up with my corner plot code. But if need be, I can get that done in a few hours and help you move forward.
Okay, thank you so much.
Daniel, from my side, so I think we've got a better idea now of roughly how many people are interested. Should we take one last break and sort of come back and discuss quickly how we've allocated people to pulsars? Or do you want to do all of that on Slack?
Yeah, I think we can do all of that on Slack. Actually, it's such a small group that it might not matter too much. So if people can just maybe even choose their own pulsars, just pick a number. Yeah, we need to invite people to the private channels that we had for each pulsar, but since there's such a small group, we could just put everyone in every channel and you could keep up to date with what's going on in the various pulsars. Okay.
So let's end the Zoom session here then, or let's take some questions and then end the Zoom session. And then Daniel and I will just have a final discussion on how to operate the Slack channels for the various pulsars. There are 5 that remain unanalyzed as far as I recall. I don't know if perhaps Daniel wants to prioritize some of them, but we can talk about that.
Yeah, I think they're all fairly equal. J13 is probably 13 something or other is probably the next easiest after 0921 because it also doesn't have much data.
Okay, so maybe we can start by adding everybody to that channel and make that be the intro pulsar.
Yeah, and yeah. So one last thing, if you're an absolute pulsar timing whiz, and this is very easy for you and you get through it all and you analyze every pulsar, then we'd be happy to look for other pulsars in your time that need analyzing. Certainly there's a whole set of all the PTA, or the pulsar timing array pulsars that we can analyze as well.
And for the other people in the group that are the least experienced and coming into this for the first time, do you suggest they do the pulsar we just mentioned?
They could do any pulsar really. So yeah, the least experienced, the only problem with J13, it doesn't have much data, so we should arrive at a solution quickly, but it's also very low signal to noise. So it's possible that we need to increase the signal to noise ratio cutoff if there's a lot of outliers, even with our current filter. So there's just one little trick that could be in that pulsar. But yeah, basically any pulsar would be fine for a beginner.
Okay, cool. Yeah, if we decide otherwise, we can still communicate groups to pulsars or whatever needs to be on the Slack channels. Are there any more questions from people online? Do you feel like you, once you are pointed to a particular directory, you have enough information to get started?
There's one question in the chat.
Oh, thanks. I'm not seeing it. In the Slack, do you mean?
Oh, the Zoom.
Wait.
Yeah. Just
which pulsar, please? Okay. Daniel, I think, an alarm. Maybe let me and you take this offline a bit and just make sure we make the best decision on how to allocate people. And then we can communicate that on Slack. So to answer the question, which pulse up, please, thanks for saying okay there. We anticipated a slightly larger group. And so I just want to rethink what's the best way with a smaller group.
Yep, sounds good to me.
All right.
Yeah, so we'll stay in contact on Slack and let you know of any updates.
Sounds good. And all of this is recorded, and so we'll just post the links to Daniel's very informative sessions this morning as well. Thanks, Daniel, for going through that. That was incredibly helpful.
That's all right. I just noticed we're not recording right now. When did the recording stop? Did you stop that?
It says recording on my end.
Oh,
At the top left. I think we're fine.
Oh, so it does. Okay. Yeah.
All right. All right, everybody.
All right. Thank you, everyone.
Cheers. Yeah.
Thank you so much.
We'll
Cheers.
chat on Slack. I hope you've learned a lot.
Okay. Bye.
Oh, yeah.
Bye.